We've just talked about discrete probability distributions. Now let's talk about drawing samples from probability distributions. So drawing samples. Oops. From probability distributions. Well, if we remember when we talked about the normal distribution, we talked about the samples going all the way from 1 to big N. And those samples looked something like this, right? And so, maybe we said the mean of the samples, their average, was mu. And maybe if we looked at the spread, that was related to the standard deviation. We didn't talk about, though, how to draw samples from probability distributions. That's a different sort of topic that we now turn to. So let's talk about the simplest possible thing. Let's imagine a stick of unit length. So the length of the stick is 1. And let's talk about, to start off with, discrete probability distribution. So let's suppose that there's some probability for some outcome, which is 0.3, and a probability for a different outcome, which is 0.7, and a probability for a different outcome, which is 0.3. Now, we're going to assume that we only have two outcomes, and sort of my pi rho 1 and my pi rho 2, as I would expect, sum to 1. Let's remove this here. And suppose that I want to draw a sample from this discrete probability distributions with two outcomes. What would I do? Well, intuitively, maybe I may think of drawing a uniform random number between 0 and 1. And if that uniform random variable, or that uniform random number that I've just drawn, falls in this bin, then I pick outcome 1. And if it falls in that bin, then I pick outcome 2. Right? So what we will say is that we will consider drawing a uniform random number. I'm going to refer to that as big U, from a uniform distribution over the range 0 to 1. And then I will compare and decide if that uniform random number, so if small u, so in other words, if the realization of big U is less than or equal to, if it is less than or equal to 0.7, then select outcome 1. Otherwise, select outcome 2. So that seems pretty straightforward. And then, of course, if I wanted to draw more than one random variable, then I would iterate on this. So I would then repeat the process, draw another uniform random variable, compare to 0.7. If it is less than or equal to 0.7, in fact, it's never quite going to be equal to, so that's a bit arbitrary. But if it's less than or equal to 0.7, then you pick outcome 2. Otherwise, you pick outcome 1. Otherwise, you pick outcome 2. Okay, well, what if I have more than one outcome? So let's talk about what happens then. So I'm going to draw my unit stick in a slightly different way. And these are going to be the outcomes. And I'm going to have outcome rho 1, outcome rho 2, and outcome rho 3. Now, if you sort of believe me for a second, I'm going to plot the probability of outcome 1. And then I'm going to draw my stick in a slightly, or if you believe I should say that this is going to be useful, I'm going to draw my stick in sort of a broken up, slightly different fashion. Suppose this here now is pi rho 2 plus pi rho 1. So I have just added to pi rho 1 the value for pi rho 2. And now by the time I get to pi rho 3, I need to add the value following sort of the sequence of pi rho 3 to the value of pi rho 2 and pi rho 1. Now, I can ask the question, what is going to be the sum of pi rho 1 plus pi rho 2 plus pi rho 3. In other words, what is this height going to be? Well, the height will be equal to 1, because of course pi rho 1 plus pi rho 2 plus pi rho 3 equal 1. This here is of height 1. Great. So now that I've done this, let me draw it a little bit more neatly without all of the annotation. I'm going to again say outcomes, and I'm going to have 3 outcomes. I'm just drawing exactly the same thing I drew earlier, but just without all sort of the messiness. So this is one step, this is a different step, this is a third step, and I know that the height of this step, final step, is equal to 1. And I will call what I'm plotting here C of rho sub m, with the understanding that that's sort of a cumulative sum of all of my pi's. So this is equal to m prime from 1 all the way to m of pi sub rho m prime. So when m prime is equal to 1, c of rho m is equal to pi rho 1. When m prime is equal to 2, then c of rho 2 is equal to pi rho 1 plus pi rho 2. So that makes sense, right? It's consistent with, this definition is consistent with the previous plot we had drawn. You're going to say, well, why am I taking my stick and sort of, instead of drawing a straight stick with 2 breakpoints, why am I sort of breaking it up as a step? Well, here's what I'm going to do, and here's why I do it. I'm going to draw a uniform random number from 0 to 1. Now, if my uniform random variable is between 0 and pi 1, suppose it's here, then I'm going to look at where this line intersects, and if it intersects at rho 1, which it will, if the uniform random variable is less than pi rho 1, then I pick outcome 2. Now, if my uniform random variable is larger than pi rho 1 plus pi rho 2, then I pick outcome 3. So this is how I'm going to draw distributions from discrete random variables. Now, the algorithm for this doesn't quite seem so clear. How am I going to, look at the intersection where this uniform random number intersects with a step, for example? So let's write it out in algorithmic form. And in algorithmic form, this will be the fundamental theorem of simulation for discrete random variables. Okay, so what I'm going to give you now is called the fundamental theorem of simulation for discrete random variables. So first, you have to start off with the notion that you have an R drawn from a categorical distribution. In other words, R is a discrete random variable. You have outcomes, and to each outcome is associated a probability, right? So what are we going to do? We are going to generate a uniform random number over the range 0 to 1. Then, and this is really the key step, we will find the lowest m such that u is less than or equal to pi rho 1 plus all the way to pi rho sub m. And finally, we will set r, the realization of a random variable, to rho sub m, that outcome. This here's the key step. So first things first, this key step, at least naively implemented, will require a for loop of some kind. And we will sort of walk through the Google Colab for the class shortly. But briefly, this will require for loop because I have to compare u to pi rho 1. And if u is greater than pi rho 1, then I have to keep going. I have to compare u to pi rho 1 plus pi rho 2. And if u is greater than pi rho 1 plus pi rho 2, then I have to keep going. So there's a loop here that I have to do. And there's a second loop required by this algorithm. And this one is maybe more obvious, maybe less obvious, I don't know. But it's the fact that, typically speaking, you're not generating just one random variable, but you're generating very many of them, and you have to iterate. So this is another loop. So sort of naively implemented, this algorithm here requires two loops. Okay. So again, let's draw graphically maybe what this would look like when we draw samples from very many random variables, discrete random variables. Again, rather than to have a stick sort of broken up into multiple parts, I create a sort of, I'm going to draw something that kind of looks plausible. I'm going to, plot my C of rho versus rho. I'm going to draw a uniform random variable between 0 and 1, see where it falls, and then pick that outcome. So rather than to draw a stick this way, I draw this step, and then I've been able, sort of the step pattern, and I've been able to relate that back to the algorithm as I've proposed it. So just one thing I think that's worth mentioning. Let's clear this here. Suppose I have two outcomes, and pi rho 1 is 0.99, and pi rho 2 is 0.01. So you're much more probable to get one outcome than another outcome. So in this case here I have rho 1, I have rho 1 and I have rho 2. So at rho 1 it jumps all the way up, and by the time I make it to rho 2 there's just a tiny little step. And the sum of pi rho 1 plus pi rho 2 is equal to 1. Now if I draw a uniform random variable from 0 all the way to 0.99, then I select rho 1. And if my uniform random variable exceeds 0.99, in that very rare case, then I select outcome 2. But wait, I have a choice. Why didn't I draw it this way? Rho 2, rho 1, and then I have a very small probability here, and then there's a massive jump there. Does it matter? And this is, of course, I'm plotting C of rho. All I've done in the second is that I've inverted rho 1 and rho 2. Does it matter which of these two conventions, whether this one or that one, that I use? Well, if I genuinely have a uniform random number generator from 0 to 1, then the probability of getting an extremely high number in this very small range should be exactly the same as getting an extremely small number in exactly this range. So in fact, it makes no difference how I order my steps. And sort of the ordering of rho 1, rho 2, or rho 3 is actually completely arbitrary. In the case of heads or tails, to make things simple, I could have referred to them as H and T, and then really, as to whether you choose to order them alphabetically or not is sort of up to you. And whether you decide to draw this sort of step pattern in this order or that order really makes no difference at all. So this brings us now to the question of how do we draw samples from continuous distributions. And before we do that, let's plot the C of rho versus rho in the case of very many outcomes. So if I have more than one outcome, and more than two outcomes, and I have very many of them, then maybe my C of rho versus rho looks like a large number of steps. And by the way, in the case of a Gaussian, the allowed values for R may be negative as well. So I can have some probability here, and then raising and going up to here. So in some sense here I'm plotting C of R versus R. and I'm plotting from 0 to 1. So in some sense, I can think of a discrete probability distribution as generating discrete steps, and a continuous probability distribution, C of R versus R, as generating sort of an infinite number sort of steps, very smooth. And this here again is always at 1, the maximal value for my C of R. So what am I going to do? Well, I'm going to draw a uniform random number between 0 and 1, and if it falls here, then I will pick this outcome. Whoops, outcome. And if it falls here, I will pick that outcome. Now, what if outcomes can be negative, like in the case of a Gaussian? So if I were to plot the P of R for a Gaussian, maybe the Gaussian has a positive mean, and it looks something like this. Then the coinciding C of R for the Gaussian, and I'm going to give you the exact formula for the C of R, may look it'll be something like this. And then here, C of R is always positive. Oops, C of R is always positive. And the maximal value, of course, is always equal to 1. What is the formula for C of R? Well, I have to sum all of my outcomes up to R, dr prime, pr prime. Now you're going to say, well, what if my P of R is an exponential distribution, and that exponential distribution has no random variable realized to any negative value between negative infinity and 0? That's fine. Encoded in the fact that you're writing exponential is the domain of the random variable understood to be from 0 to infinity. So if I were to write this down with the understanding that P of R is exponential, this is fine because I would understand that this integral here simplifies to 0 to infinity dr prime pr prime because the exponential has no domain over negative values of r prime. Now if I explicitly write lambda e to the minus lambda r, I already give it a very specific form, then I must write 0 to infinity because at this point this function here blows up when r is negative, right? But if I choose to write it more generally as dr p of r, then I can integrate from minus infinity to infinity knowing that p of r is 0 for values from negative infinity to 0. Just a small point. Okay, so what is this all going to look like, for example, for drawing samples from an exponential distribution? So let's do an example, and let's suppose that we want to draw samples from an exponential distribution. Okay? So what are we going to have to do? We consider the fact that P of R is lambda e to the minus lambda r when r is greater than or equal to 0, and it is 0 if r is less than 0, right? That's the definition of the exponential. Then I have to integrate C of R, which is going to be, well, 0 to r dr prime pr prime. And I can do the simple exponential, and that's going to be 1 minus e to the lambda r. Now here's what I'm going to do. Remember when I plot my C of r versus r, I set C of r equals to u, right? And then I try to find the outcome. So then if I set C of r equal to u, my uniform random variable that I've drawn, and then I try to find r, then I invert this equation, and I find that r is negative 1 over lambda, log of 1 minus u. Okay, now you're going to ask me, well, how do I use this expression in order to draw samples from the exponential distribution. So let's go ahead and say what we have to do. So this is drawing samples from the exponential distributions. Of course, you first draw your uniform. So I'm going to sort of use shorthand and simply say, draw u from a uniform. Whoops. Draw u from a uniform between u and 0 and 1. Then set r equal to, well, negative 1 over lambda log of 1 minus u. And you're done. Now you're going to tell me there's a negative sign here, and my r, my draws from my exponential distribution can't be negative, so what's going on? Well, remember, 1 minus u is less than 1 because u is between 0 and 1. So the log of something which is less than 1 has to be negative. And so since this is negative multiplied by negative sign, it sort of guarantees that the draw from the random variable is always positive. Now if I were to nitpick, I could also mention something else. Notice that log of 1 minus u, when I'm doing this, I'm taking 1 minus the uniform random variable between 0 and 1. But my probability of sampling 1 minus u, or sampling u, is exactly the same. So in fact, I can replace this with log u. And you might ask me, well, what advantage does that have? You avoid sort of a superfluous subtraction that you don't really need in your calculation. So if I were to sort of simplify this even further, I would simply write this down, which is exactly equivalent to what I did before. Now, the best way to verify everything I tell you is to actually sort of look at the Google Colab and play around with it and verify that this is indeed true. So, what have we gotten so far? We've explained the fact that we can draw samples from discrete probability distributions. We've also explained the fact that we can draw samples from continuous probability distributions, but that requires that we compute a C of R. By the way, the C of R has a name, and it's called a cumulative distribution, which sort of makes sense because you're accumulating the probabilities from negative infinity all the way up to R. And with that said, I think we're ready to move on to the next topic.